and then we can move on to our next talk of the session just in time. So now we have Guillaume Aubrun from Lyon, the University of Lyon, and he's going to tell us about entangleability of cones.
Okay, can you see me and hear me?
Yes, we can.
Okay, great. So thanks for the introduction. So indeed, I will tell you about a joint work with Ludovico Lamy, Carlos Palazuelos, and Martin Plavala about entangleability of cones. So what we are doing here actually is solving an old math problem, because the theorem we proved was conjectured by Barker in the 70s, and it's a property about tensor product of cones, which actually has immediate implications for GPTs. So what I will do in this talk, I will first take the conjecture and explain what it is about. Then in the second part, I will translate it into what it means for GPTs. And in the last part of the proof, I will, in the talk, I will give you some proof ingredients. Okay, so it's a conjecture about cones, or proper cones. So what does proper cone mean? So I look always at cones, proper cones, cone C inside a vector space V, which is over the real and of finite dimension. And we say that C is proper if it is closed, convex, full dimensional, so it spans V as a vector space, and salient, it does not contain the line, or if you want, 0 is an extreme point, or if you intersect the cone with its mirror image, there is only 0 in this intersection. So always, even if I don't say it, all the cones we consider will be proper. Now for proper cones, there is a nice duality. If you go to the dual space V star, you can look at the space of the set of functionals which are positive on the cone C. It's also a proper cone, and this duality is involutive. So if you take again the dual operation, you come back to the initial cone. Okay, so you probably all know that when you want to take compositions or tensor product of cones, there is not a unique way to do this. So if I have two cones, C1 in V1, C2 in V2, and I want to define the tensor product, which should be a cone inside the vector space V1 tensor V2, then there are at least two meaningful ways to do this, depending whether you think of a cone as from the inside or from the outside, because always in convexity, you have this double approach. You can think of a cone as the convex hull of some set of rays, or the set of elements which satisfy a family of linear inequalities. So if you think of the extreme rays approach, you might define then the minimal tensor product as the convex hull of all pure tensors of the form x1 tensor x2, x1 in C1, x2 in C2. So this is a proper cone in C1 tensor C2. The mean tensor product, which we denote by this symbol. And if you think from the outside, you might look at the set of elements in V1 tensor V2, which are positive when you apply to them a product of positive forms, phi1 tensor phi2, where phi1 is an element of C1 star and phi2 in C2 star. Or more indirectly, you can define the max tensor product, which we denote by this symbol here, by the dual operation to the mean. So it's the same thing as the dual of the mean tensor product of the duals. Okay, so these are two a priori distinct constructions. The mean is always inside the max. This is easy to check. And the main question today is to characterize the equality case. For which cones is there equality? And we'll say that a pair of cones C1, C2 is entangleable if these two constructions are distinct. If there is an element which is in the max tensor product and not in the mean, if there is some kind of an entangled element. So what is known about entangleability? So it's connected to the property of classicality. So we say that the cone C is classical if it is isomorphic to the cone of positive elements in Rn, R plus to the n, or equivalently if its sections are simplices, or again you can say if it is generated as a cone by the basis of the linear space V. And it was conjectured by Barker, so this is the thing which we prove, that whenever both cones C1 and C2 are non-classical, then the pair C1, C2 is entangleable. It should be, entanglement should exist if and only if C1 and C2 are both non-classical. So one direction is easy. If you have a classical cone, then no matter what is the other cone which you pair with, the pair will not be entangleable. This is something which is not hard to check. Less immediate result, which was proved actually before Barker's conjecture, is a step towards this characterization. It's an old paper by Nanyoka and Phelps from 69. So it's the following: if you give me one cone C1 which is unclassical, then I can choose another cone C2 such that the pair C1 C2 is entangleable. So of course it's weaker than the initial conjecture because you are free to choose the cone C2, which of course must be non-classical, whereas in Barker conjecture you must prove this for any given pair of cones. And for example, simple choices to prove this. The simplest is to choose C2 to be the dual of C1. Then it's really easy. What Nanyoka and Phelps did is they chose for C2 the cone over a square, or if you want the G-bit. So so here we complete this picture by showing that Barker's conjecture is true indeed. Whenever you take only two non-classical cones, then the corresponding pair is entangleable. So min and max tensor product are distinct. Okay, so let's translate this to GPTs. So we already saw today several appearances of GPTs. So I just have a quick slide to be sure we speak about the same thing. So GPTs for me will be a triple VCU. V is a vector space, C is a proper cone inside V, and we also have a unit, an element in the interior of the dual cone, or equivalently a linear form which is strictly positive on the cone except at 0. And then from this unit, you can unravel all the probabilistic theory. You can define states to be elements in C on which the unit evaluates to 1. And then once you define this, you may think of C as the cone of unnormalized states. You may define an effect to be an element which is, well, there was a nice pictures in a talk earlier today. An element in C star F, so that U minus F is also in C star. So it's between 0 and U in terms of the order of the vector space V star. And then you may define measurement to be a collection of effects which add to U. And of course, the simple examples, but important examples, are the classical theory. The cone is the positive cone in Rn, and the unit will be the sum functional, sum of coordinates. And the quantum theory, the cone will be the PSD cone, and the unit will be the trace. Okay, so of course, tensor product has to do with compositions. So now if I have two GPTs, A and B, and I want to describe the composition AB, so A is a triple V1, C1, U1, B, V2, C2, U2, then AB should also be some triple V12, C12, U12. And here there is an axiom which is quite reasonable, which is the local tomography principle. So if you accept this axiom, then it follows that actually this vector space V12 must be isomorphic in some sense to V1 tensor V2, and the unit U12 must be U1 tensor U2. So however, this axiom, or I don't think there is an axiom which will tell you what C12 should be exactly. What follows from local tomography is only inclusions. So this cone C12 for the composition must contain the mean tensor product of C1 and C2 and must be contained in the max tensor product. Okay, it should contain the mean because we want product of states to be valid states, and it should be inside the max, if you think in the dual world, because we want product of effects to be valid effects. So let's look at this equation and ask us what happens if these inclusions are strict. So if the first inclusion is strict here, this means that there are elements in the cone of states in the composition in C12. They are elements which are not separable. So in this case, the composition exhibits entangled states. Now, if the second inclusion is strict, then you can take the dual of it, and then it will follow that the dual cone C12 star will be strictly larger than the mean tensor product of C1 star and C2 star. And this means that the composition exhibits entangled effects which are not separable. So what we see from this is that if we have a pair of cones which is entangleable in the previous sense, then these two here are distinct. And then no matter which composition you take, there will be entanglement somewhere, either for states or for effects. So this is what I summarize here. Whenever you have two GPTs, A and B, so yeah, still with this local tomography behind, then any composition will exhibit some entanglement, either for states or for measurements, or possibly for both, as is the case for the quantum theory. And let me emphasize two things. So first, classicality or non-classicality, this is something which is local. It's defined for a single theory. As the opposite, entangleability is a global concept. It makes sense only for two theories or maybe more. So this theorem connects a local concept with a global concept. And the other message that we learn is that entanglement is not specific to quantum. Actually, it's universal among all non-classical theories. So somehow the exceptional theory is not the quantum one, it's rather the classical theory, which as far as entanglement is concerned, is special. Okay, so I will now move to some ingredients of the proof. So how do we prove this conjecture? So I will just sketch it, but I will try to give some hints of how it works, and maybe it will connect to things that you are familiar with. So we will use the following approach. So we have to show. So if you give me two cones which are not classical, I must give you a recipe to construct an element which is entangled. So an element which is in the max tensor product, not in the mean. And to do this, we have a gadget. So what we do, we are able to construct inside every non-classical cone something which we call rhombic states and rhombic effects. Or actually, in the paper, we don't use this name, but somehow this approach is somehow easier to explain. So I choose to do it this way. So I will define on the next slide what this means. So we are able to build these things inside every non-classical cone, and then once we have this, when we have this tool, rhombic states, rhombic effects, then we are able to, if I have this in C1 and this in C2, I can just write for you a formula which will be an element in the max and not in the mean. So I just want to say that for convenience, I will use the GPT terminology, states and effects, but but for what I want to do, there is no unit. Barker's conjecture was defined just for cone, no unit. And this lack of unit is actually an advantage, because this means that we will be able to do things, to do some transformations on our cones, which would not respect the unit. So somehow having less structure gives more freedom. Okay, so I will now explain what are these rhombic states and effects. So the states will be these elements rho I, so they live in the cone C, and the effects will be these elements Fi, they live in the dual cone C star. Now they are labeled by this strange list, so the labels are 0, 1, plus, minus, so there are 4 states and 4 effects with this label, and the first conditions explain the name rhombic, because this first line here, rho 0 plus rho 1 equals rho plus rho minus, this means geometrically that these 4 elements of the vector space V, or of the cone C, they actually coplanar, and they are the vertices of a rhombus, of a diamond, if you want. So this should hold for the states, and the same should hold for effects. So there is a rhombus of states and a rhombus of effects, and these 2 rhombi have to be somehow compatible or connected to each other by the following condition. Whenever you evaluate the effect F1 on rho 0, you get 0. And similarly, when you evaluate F0 on rho 1, F minus of rho plus, and F plus of rho 0, you always get 0, which of course you can interpret in terms of probabilities if you have a unit. And there is a last condition which is also very important, which is that each of the linear forms which you obtain by summing 2 of these effects is strictly positive. Okay, so F0 plus F plus, F0 plus F minus, F1 plus F plus, F1 plus F minus, all these linear forms are strictly positive, which means that they take strictly positive values on the cone C, except of course at 0. So let me take an example. If your theory is a qubit, so if your cone is the PSD2 cone, 2 by 2 positive matrices, then here is an example of rhombic states and effects. You can take rho 0 to be the pure state over the 0 vector, rho 1 to be the pure state over the 1 vector, rho plus to be the pure state over the plus vector, which is this 1 over square root of 2 times 0 plus 1, and rho minus to be the pure state over the minus vector. And then you can take the effects to be the same as the states. So of course, I mean, doing this takes advantage of the fact that the PSD cone is self-dual. There is no way you can do this for a general cone. But here you can do this, and all these conditions will be satisfied. So, and this also, I think, explains this choice of indices. So 0, 1, plus, minus is something which shares some similarity with these 4 states and corresponding measurements in the quantum case. Okay, so I will now make a picture because we use a lot of geometric techniques in our approach, so it's important to draw pictures. So I just summarize all the conditions in the left part here, and I will draw a picture in the affine space spanned by these 4 states. So as I said, these 4 states will be the vertices of a rhombus. Okay, so rho 0, rho 1, rho plus, rho minus. And then I have the linear forms. So I will draw their kernels. Okay, I will draw the set of points where these linear forms vanish. So there will be lines in this plane. And for example, this could be the kernel of the effect F1. So it contains rho 0. This could be the kernel of the effect F0. And I have another pair of lines which corresponds to the effects rho minus here and rho plus. Sorry, F minus and F plus. And these four lines delimit some shape, some quadrangle, which contains this rhombus. Now, where is the cone C? So, okay, so here I'm just drawing what happens in this plane. So these planes intersect the cone C, and the intersection is some convex body, which must be inside, it must contain this rhombus and must be inside this quadrangle, because the linear forms are positive on the cone. It follows that the cone, this will be the cone C, it will be inside this quadrangle. And now this last condition, the condition that when you sum two of these linear forms, you obtain something which is strictly positive on the cone. This implies that these four vertices of this quadrangle are not in C. C is not allowed to touch the vertices of this quadrangle. Okay, so this is the geometric picture which illustrates what rhombic states and effects are. So remember what we have to do. We first have to do that to prove that this exists in every non-classical cone, and then use this gadget to build an entangled element when you have two cones. So for the first part, so I will be here very quick because the argument is not so immediate, and I don't have time, so I will just give you two ideas behind. So we prove that a cone is non-classical if and only if you can build this rhombic state and effects. And to achieve this, we are mixing two techniques. Somehow each of the two axes of this rhombus are obtained by two different techniques. To obtain the first axis, the indices 0 and 1, we use convex geometry. What we do, we are doing some fine study of the facial structure of convex bodies, and in passing, we give a new characterization of simplices in this language. So of course, what we do cannot work for classical cones, and classical cones are cones for which the bases are simplices. So somehow, when doing this, we have to single out simplices, and we do this by there is some parameter which take values between 0 and dimension -1, and this maximal value is achieved exactly for simplices. So this is it for the first part, and to complete the rhombi, to build the second axis, we are using some algebraic topology. What we do is somehow we use techniques which are very similar to the Borsuk-Ulam theorem. So higher dimensional versions of intermediate value theorem somehow. So, but I don't want to say more about this, but I want rather to explain how do we construct the entangled element when we have two cones. So this is the second part of the argument. So now I have two cones C1, C2, which are non-classical. So we know that there are some rhombic states and effects in the cone C1. I will denote them by rho I and Fi. Rho I is the state and Fi is the effect. Similarly, there are sigma I and Gi, which are rhombic states and effects in C2. Sigma I is the state and Gi is the effect. And then this is the element omega, which is in the max tensor product, C1 tensor max, but not in the mean. So, of course, we are using linear combinations of product of states, but it's important that we use the minus sign, okay? Because if I had put a plus sign instead, then this element will be clearly in the mean. And this is what we don't want. We want something which is not in the mean. So we are using this formula. And if you are familiar with PR boxes, this may look familiar to you. this kind of constructions was actually already present in the old paper by Nanioka and Phelps somehow. Whenever you deal with product of squares, you will come up with these formulas. So now I have to explain why this works. So why this state omega is, why this element omega is in the max and not in the mean tensor product. So to show that omega is in the max, this is not very hard because you can just use the definition. By definition, belonging to max tensor product means that whenever you evaluate product functional, phi1 tensor phi2, product of positive forms, then it must be positive, and everything factors out, and ultimately you will have to prove an inequality about real numbers. So this is not hard. The harder part is to prove that omega is not in the mean tensor product. And here, well, how do we do this? Well, no surprise, we construct a Bell inequality. So in the usual sense, which is a linear functional which take positive values on the mean tensor product. So again, except at 0, of course, and which take non-positive value of omega. So this is, if you want, an entanglement witness or a certificate that omega is not in the mean tensor product. And how do we construct this inequality? So, okay, you probably won't have time to really digest all this, but I want to present the tools that we use, which are actually quite familiar, I guess. We are doing some elaboration on the CH-SH inequality. So starting with two linear forms, alpha 1 beta 1 on V1 and alpha 2 beta 2, we can combine them in a CH-SH manner to obtain a linear form on V1 tensor V2 by the usual formula. So plus, 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 minus. This is the usual thing. And then the CH-SH inequality can be translated in this context as follows. If both alpha 1 and beta 1 are bounded in absolute value by some linear form gamma 1 on the con C1, so if you have a bound on alpha 1 beta 1, and if you have a bound on alpha 2 beta 2, then this CH-SH quantity is bounded by twice gamma 1 tensor gamma 2, twice and not 4, as we may, if we bound naively. And this bound holds on the mean tensor product. So we apply this to the choice of functionals, which are the differences of fx. F0 minus F1, F plus minus F minus on one side, G1 minus G0, and G plus minus G minus on the other side. And we have to bound their absolute values. So of course, you can bound the absolute value of the difference by the sum. And because of these rhombic properties, F0 plus F1 is the same as F plus F minus. So it's squared well. And it follows that this linear form, twice the product of sum minus the CH-SH quantity, is non-negative on the mean tensor product.
Sorry, yeah? You just have 1 minute left, sort of. Sorry.
Okay, yeah. Sorry, I will just finish. Thanks. So this form is non-negative, and if we go into the equality case in the CH-SH inequality, you can check that this inequality, this linear form is actually positive. It's non-vanishing on the con C1 tensor C2. And the last thing is to compute the value of lambda on omega, and something very nice pops out, and you can always arrange to make this quantity non-positive. So this shows that lambda is indeed a certificate that the element omega was not in the mean tensor product. Okay, so let me just quickly summarize. So we show that non-classicality, which is something local, is equivalent to entangleability, which is something global. And in particular, entanglement for quantum is not accidental, but somehow universal among all non-classical theories. And let me just end with an open question, which is to make this quantitative. Can we find some quantities which would make this argument quantitative in terms of measures of non-classicality and of entangleability? Okay, thanks, and sorry for being a bit late.
Thank you very much. This was a very interesting result. I'm glad that you could present it to us.